Welcome to the lecture on applications of linear systems of equations. This section of notes is going to be on word problems, and we are going to be using systems of equations to help us solve these word problems. We're going to start off with a very common type of application, which are probably better known as mixture problems. So for example, we have a pharmacist needs 500 milliliters of a 20% phenobarbital solution, but has only 5% and 25% solutions available. Find how many milliliters of each he should mix to get the desired solution. So in these mixture problems, where we're combining two things to create a third, I like to draw a visual diagram to see what's going on. So I'm going to create three boxes. We're taking two mixtures and combining them to create a third. Which 2% are we mixing to create which third mixture? So if you read the question carefully, it says a pharmacist needs 500 milliliters of a 20% solution, but has only 5% and 25% solutions available. So the pharmacist is going to take a 5% and a 25% and mix those together to create a 20%. So the 5% solution is kind of diluting the 25% solution to give us that 20%. So inside of the boxes, I'm going to be writing my rates, my amounts of the concentration, and underneath I'm going to be writing my amount of liquid of each that I have. And the only amount that we were actually told in this problem was that we wanted 500 milliliters of the 20% solution. So I know that I want to end up with 500 milliliters. I don't know how much of the 5% or the 25% I need. So those are going to be our variables. Let's let x be the amount of milliliters of the 5% solution, and let's let y be the amount of the 25% solution. So if we set up our picture like this, it kind of lends itself to what the two equations are going to be for our system. The first equation just comes from this bottom row, and the fact that we are taking our x milliliters of the 5% and we are adding it or pouring it together with the y milliliters of the 25% solution, and we want that to end up being 500 milliliters total. So x plus y has to equal 500 milliliters. So this has no use of the percents at all. This is just based on the amount total that we want to end up with. So x plus y equals 500 is our first equation. Because this has two variables, we need to have a second equation, otherwise we're not going to be able to get a solution. So the second equation will use the rates of our phenobarbital solutions. So to get that equation, we're going to take the rate times the amount plus the rate times the amount, and that has to equal the final rate times the final amount. And when we do this, when we're using percents, it's a good idea to get into the habit of changing them into decimals. And remember, 5%, if you were to change that into a decimal, the decimal's right after the 5 right now, and you move the decimal 2 spots to the left, so this becomes 0.05. So we're going to want to take 0.05 times x plus 0.25 times y equals 0.20 times 500. So it's rate times amount plus rate times amount equals rate times amount. And that's how we get our second equation. Now if you do 0.20 times 500, this just equals to 100. So here's our second equation. Here's our first equation. So now we have our system. Here's our 2 by 2 system. In order to solve it, you have really two options. You could do substitution here, solve one of your equations for x or y, and then substitute that into the second equation. Because on this particular example, my x's, y's, and numbers are already lined up, I probably would just go ahead and use the elimination method. And on the elimination method, you're trying to eliminate either x or y. If I wanted to eliminate x's, for example, then I would need these coefficients out front to be the same two numbers but opposite signs. So since this bottom equation has a 0.05x, I'd want to have a negative 0.05x on the top equation, and the only way to make that happen and keep the equation balanced is to take the entire equation and multiply it by negative 0.05. So let's go ahead and do that. If I multiply through, I'm going to get negative 0.05x minus 0.05y, and then negative 0.05 times 500. Let's figure out what that is. So we get negative 25. So that's our top equation multiplied through by negative 0.05. Underneath it, let's just recopy our second equation unchanged. So 0.05x plus 0.25y equals 100. And now we should be ready to add down, and these two x terms should cancel out. 0.25y minus 0.05y is going to be 0.20y, and 100 minus 25 is 75. And then we can finish solving this by dividing by 0.2. So if we take 75 divided by 0.2, we get y equals 375. Now that's just the value of y. We still need to figure out what x is. So to do that, you would go back to your two initial equations, pick the one that looks easier to work with, and substitute in 375 for y. So out of these two, the top one here looks easier. So if we recopy this, substituting in 375 for the y, then we get 500 minus 375, which is 125. So we know x and we know y. Now because this is a word problem, it's always a good idea to write out your final solution in a sentence and to use correct units. What are these x's and y's representing? Remember, those were the amounts. So x was 125 and y was 375, and those needed to add together to that 500 milliliters. So that means the units on these should also be milliliters. So as our solution, we could write, we need 125 milliliters, that was x, so that was the 5% solution. So we need 125 milliliters of the 5% solution, and 375 milliliters of the 25% solution. And there we have it. Okay? Let's try another one. We're going to do one more mixture problem. Now, on this particular example, it doesn't look like your straightforward mixture problem because you don't have any percents showing up, but it can be treated just like the last example. So here we have a grocer who needs to mix cashews worth $6 per pound with peanuts worth $2 per pound to obtain 10 pounds of a mixture worth $3 per pound. How many pounds of each kind of nut must be used? So, just like in the last example, we can set up 3 boxes because we're mixing 2 things together to create a third. What 2 things are we mixing together? Well, we're mixing cashews, which are worth $6 per pound, with peanuts worth $3 per pound, and we're trying to obtain a mixture of the two worth, whoops, I had a typo there, not worth $3 per pound. The peanuts were worth $2 per pound, excuse me, and the mixture is supposed to be worth $3 per pound. And we wanted 10 pounds of that mixture. So 10 pounds is the amount that's going to go underneath our box. And instead of having percents, our rates here are really the dollars per pound, the cost per pound of each. Okay, so we can still treat this just like the last example. We want to know how many pounds of each kind of nut must be used. So we want to know how many cashews we're going to need, so let's call that X. We want to know how many peanuts we need, let's call that Y. And what we know is that we're pouring together X pounds of cashews with Y pounds of peanuts, and we're trying to obtain 10 pounds total. So that means this bottom row, x plus y, has to equal 10. So there's how we get our first equation in our system. Okay? Now in the second equation, we're going to use those rates, those costs per pound. We need $6 per pound times X pounds to get the total cost of our cashews, plus $2 per pound times Y pounds of peanuts, and that has to equal $3 per pound times 10 pounds total. So it's rate times amount plus rate times amount equals rate times amount. So our equation becomes 6x plus 2y equals 3 times 10, which is 30. So here's my system right here. Now to solve it, again, you could do substitution or elimination. I like to do elimination when it's already lined up. And we can eliminate either the x's or the y's. Let's eliminate the y's this time since we did x's last time. And in order to eliminate the y's, we would need this coefficient up front here to be a -2 so that it's the opposite of this +2. So that means I'm going to have to multiply this entire equation by -2 to make that happen. So if we do that, -2x plus -2y, or minus 2y, and -2 times 10 is -20. So there's my top equation multiplied through by -2. Let's just recopy the bottom equation underneath. And now I should be able to add the two equations together and get those y's to cancel out. -2x plus 6x is 4x. -20 plus 30 equals to 10. And if I divide both sides by 4, we get 10/4. As a fraction, that would be 5/2. But since we're talking about pounds, you probably wouldn't say that you would buy 5/2 of a pound. You'd probably write this as a decimal. It makes more sense to think of this as 2.5 pounds. So I would use decimals here. So we know the value of x. Once we know x, we should be able to find y by going back to the original two equations, picking the one that looks easiest to work with, which I think is this top one, and we're going to recopy it and substitute in 2.5 for x. And if I subtract 2.5 to the other side, then that tells me that y is going to be 7.5. And remember, y is the amount or the pounds of peanuts, so the units on this would also be pounds. So let's just write out our final answer as a sentence. Remember that x was the pounds of cashews and y was the pounds of peanuts. So for my final answer, I could say that we need 2.5 pounds of cashews and 7.5 pounds of peanuts. Okay, so here's one very common type of application problem, mixture problems. Another type of common application problem that you see with systems is going to be like the next two examples. These are the kinds of problems where you have a plane or a boat flying through the air or going with over a river with the current, and you have some resistance in one direction and no resistance in the other direction. So for example, we have a plane that when it flies with the wind, it can travel 4,200 miles in 6 hours. When the plane flies in the opposite direction against the wind, it takes 7 hours to fly the same distance. Find the speed of the plane in still air and the speed of the wind. Okay, so we have right in that last sentence, we're basically being told what our two variables should be. You could use x's and y's here, that's fine. I'm going to use p for the speed of the plane just to make it a little bit more obvious what it represents. And I'm going to let w be the speed of the wind. Now notice the kinds of things they're telling me in the problem. 4,200 miles, 6 hours, and we're looking for speeds, which are also called rates. So we're given some distances, some times, and some rates. And what you should remember is that there's a relationship between those three things. Distance equals rate times time. So that's kind of the overriding formula that we're going to be using for this problem. Now, because there's lots of information and lots of numbers going on here, I'm going to set up a chart, and I'm going to use this formula, but sort of in the reverse order. So I'm going to write the rates first, then the times, and set that equal to my distance, and I'm going to create 2 rows and 3 columns. The first row is going to be the plane flying with the wind. Sometimes that's called a tailwind in some problems. And in my other row, I'm going to have the plane against the wind, and sometimes in problems that would be called a headwind. So let's kind of fill in the values that we know. We were told that when the plane flies with the wind, it can travel 4,200 miles in 6 hours. So with the wind is this first row. The distance I traveled was 4,200 miles, so I can put 4,200 in the D column. And I do that in 6 hours. When I am flying against the wind, it takes me 7 hours to fly the same distance. So whatever distance I went before, I'm also doing that in the opposite direction. So this distance is also 4,200. So in these problems, they're going to tell you these 4 quantities, the 2 times and the 2 distances. For the rates, that is going to be a function of your 2 variables. So let's figure out how to write these correctly. Think about a plane flying with the wind. What does its net speed become, or what is it in terms of? It's the speed of the plane with the wind making it go faster. So it's the speed of the plane plus the wind speed. So P plus W is always going to be your rate when you have a plane flying with the wind. Now in the opposite direction, this time the wind is slowing you down, so it's subtracting away from your plane speed. So when you go in a headwind situation, it's going to be the plane speed minus the wind slowing it down. Notice here that the plane speed should always come first minus the wind. Okay, so that's going to be the same for every problem. Every plane with the wind is going to be P plus W for its rate, and the plane against the wind will always be P minus W for the rate. So we've filled out all of our values here. All we have to do next is come up with our equations, and each row going across will become an equation. When we follow our formula, remember that rate times time equals to distance. So we're going to take this rate times this time and set it equal to this distance. Because this rate is a whole quantity, we want to wrap it in parentheses. And when I do P plus W times 6, usually I write the 6 first just because it's a constant and I'm going to treat it like a coefficient. So it's going to be 6 times the P plus W, and that has to equal the distance, 4,200. Similarly, for the second row, if I wrap this P minus W in parentheses, then this rate times this time has to equal this distance, so 7 times P minus W has to also equal 4,200. Now you could distribute the 6 and the 7s across, and that's perfectly fine, but a lot of times in these problems, if you divide through by the constant coefficient out front right away, it tends to always go into this distance number equally or evenly. So, for example, if I divide through both sides by 6 on this first equation, then the 6's cancel out, so all I have left on the left side is P plus W, and 6 divides nice and evenly into 4,200, leaving me with 700. So it gives me a much simpler equation to work with. So a lot of times that's what you're going to want to do as kind of a shortcut. Divide through by your coefficient or your constant out front on both sides. So let's do that on the second equation. If I divide both sides by 7 right away, then all I have left on the left is P minus W, and 4,200 divided by 7 goes in nice and evenly and gives me 600. So you get two very nice and simple equations to work with. The other bonus here is the P's and the W's are already lined up, and because of the way these rates worked, the plus wind and the minus wind are already opposites, so I am automatically ready to add down and the W's will cancel out. So I get P plus P, which is 2P, 700 plus 600 is 1,300, and if I divide through by 2, then I get P is 650. Now that's just the value of P. We still need to find the value of W. You can get that from these two original equations over here, or you can get them from the more simplified equations over here. And that's where I like to look. So for example, if I use this one, let's recopy it a little bit neater, and if I substitute in 650 for P, then when I subtract 650 to the other side, we can easily see that the wind speed must be 50. So all we have to do now is write up our final answer as a sentence with some units. Remember that these P's and W's were speeds, and this was miles and hours, so it makes sense that these should be miles per hour. So the plane speed is 650 miles per hour, and the wind speed is 50 miles per hour. And there's my solution. Okay? Alright, we're going to try one more of those. Now this next problem is almost identical in how we're going to set it up. The only difference is instead of flying in a plane, now we're rowing in a boat. Okay? So in this example, we are told that with the current, you can row 24 miles in 3 hours. Against the same current, you can row only 2/3 of this distance in 4 hours. Find your rowing speed in still water and the speed of the current. So again, that last sentence is telling you exactly the two variables that you need to solve your problem. So I am going to let R represent my rowing speed, and I'm going to let C be my current speed. And we're told some distances and some times, and we want to know some rates, so I'm going to set up my chart. Rate times time has to equal distance. We're going to have 2 rows and 3 columns. One row is going to be rowing with the current, and sometimes that's called downstream. You know, when you're going downstream, you're flowing with the current. And then for the second row, this is going to be rowing against the current, and then that would be the same as going upstream. So your rate is going to be slower when you're going against the current than it would be going downstream. So let's fill out our chart. The time when I'm going with the current is 3 hours, and I go 24 miles. So my time with the current is 3 hours, and I go 24 miles. Against the same current, you can row only 2/3 of this distance in 4 hours. So my time is 4 hours, and to get my distance, I only went 2/3 of how far I went before. So 2/3 of 24. Let's simplify that. 3 goes into 24 8 times. 2 times 8 means I'm only going 16 miles in 4 hours. So not only am I taking an hour longer, I'm not even going as far because of that current. Okay, now we need our rates, and this is going to look very similar to our plane and our wind speed problem. In this problem, we're rowing with the current and rowing against the current. So when I'm rowing with the current, my net rate is going to be however fast I can row plus the current at my back, making me go faster. When I'm rowing against the current, it's however fast I row minus the current slowing me down. So those are my two rates. It looks just like our P plus W and our P minus W, except this time it's R plus C and R minus C. So very, very similar. Now to get our two equations, we're going to wrap these rates in parentheses, and we're going to do this rate times this time equals this distance, and do the same thing for the bottom row. So our first equation, taking the top row, is 3 hours, I'm going to put that out front, times my rate, r plus c, and that was equal to 24. The bottom row becomes 4 hours times r minus c, and we only got 16 miles. Notice that 3 divides evenly into 24, 4 divides evenly into 16, so let's do our little shortcut and divide both sides by those coefficients so that we get a little bit cleaner equations to work with. If I divide through by 3, then we get r plus c equals 8. If I divide the bottom one by 4, then I get r minus c equals 4. And these already have the c's being opposites, so I am ready to add down right away. The c's will cancel out. R plus r is 2r. 8 plus 4 is 12. If I divide by 2, then r equals 6. Now we need to find c, so go back to either of these two or either of these two more simplified ones. I usually take this one right here, r plus c equals 8, and we can now substitute in 6 for that r. So if I subtract 6, then my current c is 2, and appropriate units here, again this was miles for distance and hours for time, so these are going to be rates that are miles per hour. And if I write out my final answer, it looks like we have a rowing speed is 6 miles per hour, and the current speed was 2 miles per hour. And there's my final solution. Okay? Alright, we're going to do one more 2x2 system problem, and this one is kind of a geometry application. So we have a rectangular lot whose perimeter is 320 feet, and it's being fenced along 3 sides. An expensive fencing along the lot's length costs $16 per foot, and an inexpensive fencing along the lot's 2 side widths costs only $5 per foot. The total cost of the fencing along the 3 sides comes to $2,140. What are the lot's dimensions? So we're talking about a rectangular lot. It makes sense here to draw a picture. So let's draw a big rectangle. We are told that the perimeter of this rectangle is 320 feet, and we are looking for the 2 dimensions, so let's call this length and this width, and let's write in some of the things we know. We know that we're only fencing along 3 sides. We have inexpensive fencing along the lot's length, so this side here is $16 per foot, and an inexpensive fencing along the lot's 2 side widths only costs $5 per foot. Now we aren't fencing along this 3rd side, only these 3 sides here, not along the 4th side. Maybe the house is on this side, for example, which means we don't need to have fencing along that side. So here's our picture. So we need some variables, and in this problem, since we're looking for the lot's dimensions, we need to know the width and the length. So let's use L for length and W for width. So we're looking for those. And now we need to come up with 2 equations. We've got 2 different types of quantities given to us. We're told a perimeter, 320 feet, and we're also given total cost, which is $2,140. So one of these equations is representing feet, and one of these equations is going to represent dollar amounts, costs. So the first thing we have to remember, let's start with perimeter, is a formula for perimeter of a rectangle. Perimeter of a rectangle from geometry is 2 lengths plus 2 widths, because perimeter is all 4 sides added up. Now, even though we're only fencing 3 sides, the perimeter here still counts all 4 sides. So we're going to use that equation and basically plug in what we know. We know that the perimeter is 320, so we're just going to substitute in 320 in for that p. So our first equation is 320 has to equal 2 lengths plus 2 widths, and that comes straight from perimeter. Okay? For the second equation, we're going to use these costs. Now think about how you would tally up your total cost. We have one length that's going to cost us $16 per feet. So if the length L is L feet, then we would need L feet times $16 per foot, and that means our cost of just this long side is going to be 16L. Plus, we have this side over here, which is W feet long at $5 per foot. So that cost would be 5W, and I have 2 of those 2 sides that are equivalent. So you could write 2 of these 5Ws, and that total cost needs to equal $21.40. Now I'm putting the numbers here on the left side. It's perfectly okay if you put them on the right side as well. Okay, so again, here's our total cost. $21.40 is $16 times L feet plus 2 $5 times W feet. So there's our 3 sides all tallied in. And if we kind of simplify this a little bit, we get $21.40 equals 16L plus 10W. And our top equation again was 320 equals 2L plus 2W. So here are my 2 systems, my 2 equations for my 2x2 system, and everything's nicely lined up, so it makes sense to use elimination. Let's say that we wanted to get rid of the L's, then I would need this L up here to become a negative 16, and in order to make that happen, I'm going to have to multiply the equation by negative 8. So let's go ahead and do that. Negative 8 times 320, let's figure that out. Negative 8 times 320 is negative 2560. Negative 8 times 2L is negative 16L, and negative 8 times 2W is negative 16W. So there's the top equation multiplied through by negative 8. Let's just recopy the bottom equation, and I should be ready to add down, and these L terms are going to cancel out, and we need negative 2560 plus 2140, and that's going to be negative 420, and negative 16W plus 10W is negative 6W. If I divide both sides by negative 6, then we just get 70. So we now know what W is. Now we need to figure out L, and then we'll be done. So to find L, you can go back to your 2 initial equations here and pick the one that looks easiest to work with. I'm just going to use this top one, the one from the perimeter. 320 equals 2L plus 2W, and I'm going to substitute in 70 for that W. So 2 times 70, that's going to give me 140. If I subtract 140, then 320 minus 140 gives me positive 180. And if I divide that by 2, we get L equals 90. So we have our W and our L, and now we're ready to just write out our final solution. Remember that these were dimensions, lengths and widths, and the units that we were using were feet. So we could just say the dimensions of the lot are 90 feet by 70 feet. and there is our solution. Okay? So to finish off today, we're going to do two last examples, but this time our last two examples are not going to give us 2 by 2 systems, they're going to give us 3 by 3 systems. So 3 equations with 3 variables. So let's take a look at this first problem. 3 numbers are unknown, so let's call them x, y, and z. 3 times the first number plus the second number plus twice the third number is 5. So right away, we can translate that into an equation. We're going to let x be the first number, y be the second number, and z be the third number. So we want 3 times the first, that would be 3x, plus the second number, which is y, plus twice the third number, so that would be 2z, is, or equals, 5. So there's our very first equation. Second sentence here, if 3 times the second number, remember the second number was our y, is subtracted from the sum of the first number x and 3 times the third number z, the result is 2. Okay, so let's translate this one. This one's a little bit tougher. 3 times the second number, so that would be 3y, is subtracted from. Remember when you see the phrase subtracted from, you kind of have to remember to switch the order around. So 3 times the second number, or 3y, is getting subtracted away from stuff. So we're going to put our minus sign down, and 3y should come after the minus sign so that it's getting taken or subtracted away from our stuff. And what stuff are we subtracting it from? We're subtracting it from a sum, the sum of the first number and 3 times the third. So we're subtracting x plus 3z minus 3y, and the result is 2. So that one's a little bit harder to do. That's our second equation. Now for the last sentence, if the third, remember that was our z, is subtracted from 2 times the first, that was our x, and 3 times the second, that was our y, the result is 1. Okay, so the third is subtracted from, so put your minus sign because we saw that word subtracted from, and the third is getting subtracted away from, so minus z, and it's getting subtracted away from 2 times the first, 2x, and 3 times the second, 3y, and the result is 1. So here is our 3 by 3 system. Now before we jump right in, you need to notice that your x's, y's, and z's are not totally lined up correctly because in this middle equation, the z and the y term are sort of backwards. So the first thing we need to do is swap these guys around. So I'm going to leave the x in the front, but then I'm going to put the minus 3y second and the plus 3z third, just so that it lines up with the other two equations. And let's go ahead and recopy those. So here's my new system. Now the first thing we want to do in a 3 by 3 system is figure out, based on our coefficients, which variable looks easiest to eliminate. And if you look at your x coefficients, your y coefficients, and your z coefficients, probably y would be easiest because these two right here are already opposites, so they're going to eliminate right off the bat. So let me call this equation 1, equation 2, and equation 3, and I'm going to eliminate y. Now when I eliminate y, you're going to pick 2 equations and eliminate y from them. So I'll start with equation 2 and equation 3 because those were the 2 that I didn't have to do anything to first. So I'm going to recopy equation 2, unchanged, and then let's recopy equation 3, unchanged, and now I can add down right away, and the y's will cancel out. X plus 2x is 3x, 3z minus z is plus 2z, and 2 plus 1 is 3. This becomes our first equation in our 2 by 2 system. So we start with a 3 by 3 and we try to narrow it down to a 2 by 2. We need another equation over here in order to be able to solve this 2 by 2 system. So we're going to go back over to our 3 by 3 system. Remember that we already used equation 2 and equation 3. We haven't used equation 1 at all yet, so we have to use that one next. And if I want to use equation 1, then one thing I could do is, if I used it with equation 2, multiply this equation 1 by 3 so that I get a 3y here, which will cancel with this minus 3y. So we're going to use 3 times equation 1 and equation 2. So let's find out what 3 times this top equation is. We get 9x plus 3y plus 6z equals 15. And the second equation, unchanged, is x minus 3y plus 3z equals 2. So if I add down, the y's cancel, and I get 10x plus 9z equals 17, and that's going to join this one over here. So now I have my 2 by 2 system right here. So my next task here in solving this is, now that I've eliminated y, I'm going to need to either eliminate x or z, whichever looks easier. And in this case, they both look equally tough. So let's try eliminating, let's say we want to eliminate x. Doesn't really matter which one you do. But if I want to eliminate x, then I need these two front numbers to be the same number but opposites. And 3 and 10 don't really have anything in common, so the greatest common factor that I could get for both of them would be 30. And to get a 30, I'm going to need to multiply this top one by 10 and this bottom one by 3. That's going to give me both of them to be positive 30s, so we need to make one of them negative. It doesn't matter which one. I'll just make the top one negative. So this new top equation, when I multiply by negative 10, becomes negative 30x minus 20z equals negative 30. If I multiply the bottom equation by 3, I get 30x plus 27z equals 51. Now when I add down, the x's cancel out. Negative 20 plus 27 is 7z. 51 minus 30 is 21. And if I divide by 7, we get z equals 3. Now once you have z, there's only one variable that you can find next. Think about which variable must you find next. If you go back to your 2 by 2 system, we know z, and the only other variable in this 2 by 2 system is x. So once we know z, we should be able to find x. So that's what we're going to do next. Now, out of these two equations, the slightly better looking one, I think, would be the top one because the numbers are a little bit smaller. So I'm going to recopy it. And we're going to substitute in 3 for z. So we get 3x plus 6 equals 3. So we get 3x equals negative 3. So x equals negative 1. So we know x, we know z. Now what's left? We need to know y. To get y, you've got to back up one more step back to that original 3 by 3 system. So out of these 3 equations, we're looking to solve for y. Which one has the simplest y? I would say this top one because it has a coefficient of 1. So I am going to use that top equation right there. I'm going to recopy it. And I'm going to substitute in x. We know x was negative 1. We don't know y yet, so leave it as y. And z was 3. So I'm going to substitute in 3 for z. So we get negative 3 plus y plus 6 equals 5. Adding like terms, negative 3 plus 6 is 3. And if I subtract 3, we get y is 2. So our final answer, we found x, y, and z. These were our 3 numbers. So the 3 numbers are -1, 2, and 3. Okay? Alright, so that's a 3 by 3 system. A little bit tougher to do because the process of solving a 3 by 3 system is a lot more involved. You just have to be very careful and organized. We're going to try one last example that is also a 3 by 3 system, and this is also kind of a geometry related problem. So in this example, we're trying to find the values of x and y in the following triangle. So if we have this picture given to us, what are some of the things that we know about this picture? It doesn't really matter what order you deal with this, but the first thing that I see is a triangle with angles x, y, and z. And one thing that we want to remember about triangles is that the sum of 3 angles in any triangle is always 180 degrees. So right away, that gives me one equation to work with. X plus y plus z has to equal 180 degrees. So there's one equation. Now another equation would be coming from these two angles right here. Notice that angle y plus angle 2x plus 5 adds up to this straight line, which is a 180 degree angle. It's called a straight angle. So y plus 2x plus 5 also has to equal 180. Similarly down here, these two angles also form a straight line, so they have to add up to 180 as well. So z plus 2x minus 5 has to equal 180. So here are my 3 equations with 3 variables. Now they're not quite cleaned up enough, they're not quite organized in the right order. So for the second one here, one thing I would want to notice is that I could subtract that 5 over, and I also probably want to line up my 2x and my y in alphabetical order. So let me write this down here. My top equation I'm not going to do anything with. That one's just fine. But this second equation, when I swap the 2x and the y just to put them in the correct order, and if I subtract that 5 over to the other side, 180 minus 5 is 175. So this second equation just turns into this, and now it's a little bit cleaner. For the third equation, we're going to add 5, and I'm going to, again, swap the order here. 2x comes first. I'm going to put the z over here, leaving a little space to notice that there's no y term, and 180 plus 5 is 185. So here's my new 3 by 3 system. Now in this system, what you can notice is that 2 of these equations only have 2 variables. So take the help where you can get it. Pick either the middle one or the third one and keep it the same. It doesn't matter which one you use. Let's say that I keep the second equation. That's going to become the first equation in my 2 by 2 system. And this is my 3 by 3. So if I'm keeping that one, then I have to use the first one and the third one, the other two that I haven't used yet, and I need to make sure that I eliminate z from these other 2 equations, because there's no z showing up in this equation that I'm keeping over here. It just has x and y. So we want to eliminate z from equation 1 and equation 3. And that's pretty easy to do because the z's are already the same number. We just need to get some correct signs in there. So if I multiply this top equation by -1, then that'll get me the z's to be opposites. So this top equation times -1 becomes -x minus y minus z equals -180. And the bottom equation lined up underneath, unchanged, is 2x plus z equals 185. So if I add down, 2x minus x is x. I have this minus y, which just carries down, and the z's cancel out, and 185 minus 180 is 5. That's the second equation that's going to join my system over here. So here's my new 2 by 2 system. They both have x's and y's. And notice the y's are already opposites. So all I have to do is add down, and the y's will cancel out. 2x plus x is 3x. 175 plus 5 is 180. And if I divide by 3, x equals 60. And this is an angle x. So this would be 60 degrees. So we now know what x is. What variable must we find next? If you look back at your 2x2 system, we know x. The only other variable in the 2x2 system is y, so we're going to have to find y next. So pick either of these equations, whichever one looks simpler. I kind of like this one right here. If I recopy it, and I'm going to substitute in 60 for x, if I subtract 60, I get minus y equals negative 55, so positive y equals positive 55, and this is also an angle, so 55 degrees. Okay, now we have x, we have y, all we need left is z, and to get your third variable you have to go back to your original equations and substitute in. You can use any equation you like. I couldn't use the middle one here because it doesn't have a z, but I could either use the bottom one or the top one. Let's say that I use the top one. If I recopy it, and I can substitute in now 60 for x and 55 for y, and that should enable me to solve for z. So 60 plus 55 is 115. And if I subtract 115, then I get z equals 65. And this is another angle, so 65 degrees. So my final answer, x is 60 degrees, y was 55 degrees, and if you look back at the original problem, it just wants to know the values of x and y, so I really didn't even need to find z, but it's kind of a nice practice to do it anyway. So x is 60, y is 55, and that's all they wanted to know, so there's my final answer. Alright, that concludes our lecture on applications of linear systems of equations. Good luck.